Hey everyone, in this video I'm going to talk about the properties of composite functions, which is the last Newton assignment for section 1.4. And this one has a couple tricky types of questions. So the first is decomposing a composition, so kind of looking at the end result and trying to figure out what two functions it could have come from, and then finding domains of these compositions. Okay, so let's start with one where we're decomposing a composite function. And first of all, this is a really important skill that you'll need in calculus. When you're taking derivatives of composite functions, you'll have to be able to break them down to use what we call the chain rule. So that's part of why we're kind of focusing on this in this section. And so one thing you can do when you first look at this, you can kind of see if you can figure out what your inner function, right, which in this case would be your g of x is, right, and then your f of x. And so if I were to just pick something that's the inside function, right, that looks like this expression that's plugged in here, right? So maybe I might say g of x then has to be that negative 3x plus 9. And then to see what I'm plugging that into, right, ignore the highlighted part. That would mean what I'm plugging into is the square root of the input plus 2. Right, so to me that's the most, if you were to see one of these, that's kind of the first one that you might identify, which it looks like is, let's see if that's one of our choices. It looks like that's the third choice here. Right, but I also want to point out that this says to select all that apply. So it's not just multiple choice, right, where we're just looking for one correct answer. And fortunately, they were kind here. They told us that there are two that work, right? So we found one of them. So for the others, I would just suggest really going through and seeing if each one works by doing the composition. So this next one, if we were to find f of g of x, right, we would be taking this whole g function and plugging that in for the input here. So that does actually looks like it would work, right, because that would give us the g function, right, gets plugged in to that spot, and then we add 2 to it. Right, so actually, since they told us two choices work, I already have found them, but you could go ahead and check through the others just to see, right? So the next one, again, we're taking this whole g expression and plugging it in right there. So this one does not look like it will work. It has kind of all the right components, the negative 3, the square root, the plus 2, right, but they're not in the right order. So this one is not a match. And again, you could just keep going through each of the other choices to check when I actually compose it, does it match the original function? Okay, so now let's talk about these domain problems. So with the domain of a composition, the reason it's tricky is because remember that when we do these composition functions, right, when we find f of g of x, that means that we're applying the two functions in sequence, right? And in this case, we would be taking the x and plugging it into the g function first, right? Then taking that result and plugging it into the f function. Okay, and then finally on the other side, we get our output of the composition. Okay, so the tricky thing is that we have to be considering both domains, but even beyond that, we also are checking with this second function. We're not just making sure our x is in the domain of f, right? But we're making sure that whatever comes out of that g function is going to be able to be plugged into f. So remember, the two things that we're always checking is first, x has to be in the domain of g, right? Otherwise, we can't even get through step 1. And then the second thing we have to check is that g of x, right? The output of that first function has to be in the domain of f. Okay, so that's the general process. So before we apply that to this problem, let's step back and see what our restrictions would be here for f and for g. So for f of x, we're dealing with a rational function, right? This fractional expression. And so we know that there, the problem we're trying to avoid is that the denominator can't be 0. So if we just take this denominator and say that that can't be 0, if you solve for x, that means that x can't be equal to 3. So that's our domain restriction for f of x. And then if we do something similar for g of x, with g of x, the problem we're trying to avoid is that the thing under the radical we know can't be negative, so we need it to be greater than or equal to 0. And again, if you solve for x, that tells us x has to be greater than or equal to 2. Okay, so these are the two pieces that we're working with, but we don't just put those together. We have to see how that fits in with what we've written down here. So since step 1 is that x has to be in the domain of g, right? We're looking at this restriction. And that's just the restriction for x, right? Because x is going right into the g function. But when we get to this restriction for f of x, remember, it's not x that we're plugging into f, but the output of g. So what we're trying to make sure doesn't happen is that our g of x can never be equal to 3, since that's the thing we're plugging into f. So at this stage, we can write down, okay, well, what is g of x? And now we just solve for, if we know that that output of g can't be 3, what input, what x value do we have to avoid from the beginning? So to solve this equation, we could square both sides to get rid of the square root. We could subtract the 6 and then divide by 1. Right? And so notice that doesn't match the statement we had up here. It's not just that x can't be 3, because in order to make sure g of x is not 3, this is actually the original input that we're trying to avoid. So this would be our final domain, putting these two pieces together. So all numbers greater than or equal to, oh, and I'm sorry, I made a mistake up at the very beginning with my sign. When I subtracted that 6 over, it should have been a negative. So this should have been -2. So our statement should say all real numbers greater than or equal to -2 other than 1. So that would be this final choice down here. So this is another composition domain. So I'm again going to draw that diagram, and it's important though to notice what order your composition is in, right? So this is also f of g of x, which means I can draw the same picture I had before, right? Because x is going into the g function first, and then the output of g is going into the f function, right? So again, if it was g of f of x, we would have to change the order here. Okay, and again, this means what this diagram shows us is that the two things we're looking out for is, first of all, our x has to be in the domain of g, right? And then whatever we get out of g, right, g of x, has to be in the domain of our f function. Okay, and now that we have our setup, we can pause there for a second and go back to the two individual functions to see what restrictions we're dealing with here. So, oops, just undo that, sorry. Okay, so before we add anything else to this diagram, we can go back and see what the domain restrictions were for our two individual functions. So these are both rational functions. So for both of these, we're just trying to make sure that the denominator expression is not 0, which would mean in this case that our x can't be, or our input can't be -2. And for g of x, if we subtract the 6 and divide by 8, that would mean that our x can't be equal to -3/4. Okay, and so now we just have to figure out how to, work that into our diagram below. So for x being in the domain of g of x, right, that just means that this restriction has to be true for our x, right? So it's just exactly our x that can't be equal to -3/4, right? But remember, for the second step, it's not actually that our x can't be equal to -2. It's that whatever we're plugging in, which is g of x, can't be equal to negative 2. Right? So now I take my whole g of x function, 1 over 8x plus 6 equals negative 2, and I have to solve this equation for x. Okay, so sometimes this might be a fraction, right? Or you could even write it as a fraction and then cross multiply. Or in this case, I can just multiply the the 8x plus 6 over to the other side. Okay, and I just move things around to make a little more room here. And so now we could distribute that negative 2. And then I would add the 12 over, which would give us 13, and divide by negative 16. So we get negative 13 over 16 as our restricted value here. Right? And so remember, to construct our final domain, we have to respect both of those restrictions. And so if you were doing this, if we were trying to write this in, say, interval notation, right, we would have to maybe picture a diagram here. This is saying that x can't be equal to negative 13 over 16, and it also can't be equal to negative 3 over 4. Right, so those would be open circles. But we would be able to have everything else, so everything below negative 13 over 16, between the two values, or above negative 3 over 4. So if we had to write this in interval notation, we would have these 3 pieces. Okay, but I think for most of the ones on Newton here, it just gives you more of a statement of all values except, so these are just the 2 excluded values. So I think, yeah, the choices would be something like this. And so our answer would be this one, all real numbers except those 2 problem values we identified, the negative 3 over 4 and the negative 13 over 16.